Okay, hi everyone, and welcome to the lecture 3, part 2. And part 2, we're just going to be continuing with from where we stopped in the last part, which was 1. So, we're going to continue from mass relations in reactions. Mass relations in reactions. So, what's the reaction? Reaction is simply where you get your reactants together and then you get the product afterwards. Put your reactions together in the analysis, because we talked about chemical analysis. A chemical analysis will involve a reaction, and it's all called experimentation, where you're experimenting. You have a reaction and you have reactants coming together to form products. So you have your reactants on the left hand side, products on the right hand side. I don't know, yeah, left and right, which is your left and my right. So chemical equations are represented with chemical reactions. And you have your reactants on the left and your products on the right. So in this case, we're trying to ensure that the equations must be balanced. You must have number of atoms, equal number of atoms on both sides, and equal number of elements on both sides. Each of them has to be balanced up. Sorry, made that mistake again. So writing your equations is very important. Very important that when writing your equation, there are certain things you put into consideration so that there are rules you have to play by. So you must know the reactant and then resulting products from the reactant. You don't jump into a reaction without possibly knowing what the outcome will look like, because bad chemistry is just reacting stuff without knowing what the possible outcome is. People have gotten hot just doing that blindly. And when a reaction is a vigorous reaction, you are careful to set the atmosphere to be able to contain. If a reaction can result in some form of explosion, you have to have a contained environment where whatever it is the product will be contained in a sense. So often necessary to do an experiment analysis to determine the products of the reaction. So that's been said, let's just move quickly to the part 2. First and foremost, what we do is that we write a skeleton equation for the reaction. By skeleton reaction, it doesn't mean you drawing a skeleton or something. It just simply means you just writing what the basic reactants and what your basic products will be. And then when you have done that, you include the state, whether it's solid, whether it's liquid, whether it's gaseous. You include that on both sides, and then you now start balancing. And by balancing, what you do is that you change the coefficients. I'll explain what the coefficients are. They are attachments to the products and the reactants that you can tweak, and that's the only thing you can tweak. That's the only thing you can adjust. You can adjust what the reactants are and what the products are, but you cannot adjust the coefficients. So it's best to balance the elements that appear once. So what is advisable is that you do the elements that appear once first before you go for the multiple ones, because once you fix those ones, other ones will fall through. Because if an element appears several places, you might get confused. You might be turning in the back and front. So we have an example, and it says crystals of sodium hydroxide react with carbon dioxide from air to form a colorless liquid, water, and a white powder, which is sodium carbonate, which is commonly added to detergent as a softening agent. So write a balance equation for this chemical reaction. So what this is your crystals of sodium hydroxide reacted with carbon dioxide in air, and then it forms this colorless liquid, which is water, and the white powder, which is sodium carbonate. So understand that the colorless liquid is not one of the reactants, as I used to tell the students jokingly. The colorless liquid is not one of the reactants. Water Sorry, it's not one of the products. Water is a product and sodium carbonate. Notice that they say the colorless liquid, comma, water, and a white powder, comma, sodium carbonate. So it's there for a reason. The comma just goes to emphasize what it was. So we now then translate all the story that was written in this place into a reaction. And it's funny how you have a whole gist that can turn into a simple reaction that is just one line. This whole thing turns to something that is one line. And notice the states of the things: crystals, solid, and then the carbon dioxide, gas. So notice that this is what it will look like. First, draw the skeleton equation. You write it down: sodium hydroxide, CO2, Na2, CO3, and then H2O, which is the water. So you do that first, then you put the states. You know that the sodium hydroxide is solid, the CO2 is gas, the powder is powder, so it's solid, and then the H2O is liquid. So once you're done with that, you've set the state, then you now ask yourself, is it balanced? Check the number of sodium here and the number of sodium here. You notice that it's already off. This is 2 and this is 1. So hence, if you add 2 here, now you have 2 sodium here and 2 sodium here. Then what else are you looking out for? Let's look out for hydrogen, because we have 1 hydrogen. So you have 1 hydrogen, you have 2 hydrogen here currently because you have added 2. You have 2 hydrogen here and 2 hydrogen here, so it's balanced. And then you look out for carbon. You have 1 carbon here and 1 carbon here, which is balanced. And then look out for oxygen, which is 2 plus this, which is 4, which is 3 and 4. So it means it's balanced on both sides. Just to do the check: hydrogen 2 on this side, 2 on this side. Carbon 1 on this side, 1 on this side. Sodium 2 on this side, 2 on this side. That's the left and the right. Then oxygen is 4 and 4. So hence you have the balanced equation written as such. So 2 moles of the sodium hydroxide, and then reacting with CO2, and then you have your sodium carbonate, and then you have your water. So that's how you do the balancing. So you have mass relations in equations. Mass relation equation. So the coefficients of balance equation represent the number of moles of reactants and products. So we say the number of moles of reactants and products is what makes up the coefficient. Remember this, I told you the numbers you attach in front of the reactants or the products is the coefficients, what we call the coefficient. So changes to this is what happens on the left and right when you're balancing equation. So just looking at mass relation, and look at this very closely. Notice that you have 2 moles of the dinitrogen hydride and dinitrogen tetraoxide here. You have no moles, and then all of a sudden you have 3 moles of nitrogen and 4 moles of water. You'll be wondering, total here you have 3 moles of everything. There's 2 of this and 1 of this. And now you have 7 moles of everything on this other side, and you should be asking yourself, how? 3 moles here, now you have 7 moles here. What went wrong? Well, notice that the mass will still be intact on both sides, because you have 2 of the nitrogen, 4 of the which is 8 now, and then you have 4 here, 2 here. Notice that what just changed was what was in front, because now this is H2 and then this is 3 moles of N2, sorry, and this is 4, which is quite fair because you have 8 and then you have 4 of this now, so it means that it's very much intact. So 2, 1, and then 7 at the end of the day is a lot to take in if you don't understand the fact that the elements themselves have their mole amounts. So the flow chart just shows what's given and what's asked for, and you have your mass and mole relations between the two. I'm just trying to balance the ratio of what you're given and what you're asked for. That's just your conversion through that. It's not well on that. So we have an example of ammonia, and ammonia is used to make fertilizers. So ammonia is one of those ingredients. You get them from animal dung, and most times they can use them naturally, or sometimes they can actually process them. So they use ammonia as fertilizers because of the nitrogen, rich nitrogen present in ammonia, and hence use that to as a source of nutrients to the plants, because the plants have bacteria that fix nitrogen into them, nitrogen fixing bacteria as they're called. So you have for lawns and gardens, by reacting nitrogen gas, so the ammonia fertilizers, they use them for lawns and gardens, and by reacting nitrogen gas with hydrogen, you have the ammonia. So the balance equation for this reaction is seen here. We have the N2 gas and then the 3 moles of hydrogen to give you 2 moles of ammonia. What we said earlier, this is 4, and then you end up having 2. It is 1 and 3, which is 4, and then you have 2 moles at the end of the day. So the question is, how many moles of ammonia will form when 1.34 moles of nitrogen react? Very interesting. So how many moles of ammonia will form when 1.34 moles of nitrogen react? Very important that you understand that the question is, if you change the amount of nitrogen, what will be the product? Amount of nitrogen, what will be the product? Because you know that 1 mole of nitrogen is what gives us 2 mole of the ammonia. Hence, 1.3 mole of nitrogen will give us how many mole of ammonia? That's the question. So hence, if you do that effectively, you will see that the 1 and then the 2, when you multiply it by the 2, you have your 2.68. If you cross multiply, because that thing I just showed you now is basically cross multiplication. If 1 mole of nitrogen will give you 2 mole of ammonia, then 1.34 mole will give you X. So you just 1.34 mole multiplied by 2 and then divide by 1. So hence you have this value. That's a more logical way to look at it if you don't want to use this to work it through for yourself. So I will round off going down on the route of limiting reactant and theoretical yield. I'll explain this straight off the top. When you say limiting reactant, you're looking for the reactant that actually limits the reaction, and then theoretical yield is the yield you should get in theory. I used to say this to students, it's very easy to cook a meal with your words. You can just say, oh, you just put it on the fire, you do it. It's very easy, it looks, but the real stuff itself is hard work. So hence in theory, it's quite easy. Just say, okay, when you react this is the amount you get. Or the experiment is the work. But just put that at the back of your mind when we get to experimental yield, will make sense. So in theory, when you have SB, what's SB again? What's the element? SB. For those of you that started off from the beginning, we talked about it a lot. So some of you got it already. It's antimony. SB is antimony. I think if you look very closely, you can see. So you have SB, and then I, which is iodine, and the SB is your antimony, and it's your powder. It's a powder, your dark gray powder, and then your iodine is a violent in color, which is almost like purple violet. And then when you mix the two together, what you get is reddish. And this is to explain what I said before when we started the course. The two reactants are nothing like their products. You should think that if you have a dark gray powder and then but you should get something close to violet, maybe a brighter violet or a darker, or you have red, mean that the reaction produce the product that is very different from the reactant. So the reaction, and the reaction as well, is a vigorous reaction, meaning that the reaction produces a whole lot of activity. You can see a lot of activity in the process, it fumes, and then you now get this product, which is a solid. So solid. So that's the product, and the product is antimony iodide. Yeah, going by the name. So 2 moles, 3 moles. You see, it gets complicated when you think about it. 2 moles of antimony, 3 moles of iodine, which is 5 moles, and then at the end of the day you just have 2 moles of your product. So it's quite interesting when you think about it. So the approach to limiting reactant problems is to calculate the amount of the product that will be formed from the first reactant we're completely consuming. The first reactant we're completely consumed, then you repeat for the second reactant, and the goal is for you to find which is smaller. So you choose the smaller, which of them will produce a smaller product, and then that is your limiting reactant. So the limiting reactant, and the smaller of them is your limiting reactant, and the resulting product is your theoretical yield. So your theoretical yield is from your limiting reactant, which is the smallest, which what produces the least amount. So that's that. So we have an example which is based off the imagery we just saw not long ago of antimony and iodine reacting together to give you antimony iodide. So notice that from the reaction, they said what is the limiting reactant and theoretical yield. So when 1.2 mole of antimony and 2.4 mole of iodine were mixed or are mixed. So notice that 2 mole of antimony will give you 2 moles of this whole compound. So it means if that is 2, you have 1.2 moles of SB to give you X of this, because you're trying to find what the yield will be. So once you do that, notice that the 2 will cancel the 2, and then you have the same 1.2 as the product. Then for the 2.4, notice that it's 3 to 2, and then 2.4 will give you what value? I think it's 1.6. Yeah, 1.6. So notice that I didn't have to go through. So notice that when this cancels out, you have your 1. When this cancelled through, you have your 1.6 mole. Between the two, which is bigger? Obviously, which is smaller, sorry. Obviously, you have 1.2 as a smaller value. So that is obviously our limiting reactant, because 1.2 is less than 1.6. So that is our limiting. So antimony is our limiting reactant. So, and what is the product of our limiting reactant? Is 1.20 mole. That's the theoretical yield. So our theoretical yield is the amount of antimony iodide gotten from our limiting reactant, which is still 1.2 as well. So that's how you work out your limiting reactant and theoretical yield. So that's what we call the experimental yield. Experimental yield, as the name implies, is what you get when you have done the experiment. So the quantity of the product measured after performing the reaction in the laboratory is what you call your experimental yield. So the experimental yield are always lower than the theoretical yield, and the question is why? Why are they always lower? The reason is because some of the products are lost with competing reaction. That's all the reaction that's taking place alongside it. So it's lost that way. And some of them are lost through handling. They're lost through handling. Maybe you're trying to pour it and some of it fall off. You had weighed it, but some had fallen off. It's not part of the reaction, so it will be lesser. And some of the product may be lost through separating in a reaction mixture. Sometimes if their products are gaseous, you just have them escaping as well. And that's what we call your percentage yield. And the percentage yield is obviously your experimental over your theoretical multiplied by 100. That's the percentage yield. So experimental, which is your E, over your T multiplied by 100, which gives you your P, the percentage yield. Here we have an example that we'll run through quickly as the last thing before the end of the course. So this example now says consider the reaction between magnesium and iodine to produce magnesium iodide. So student determines by calculation that with the amount of reagents he has in hand, he should produce 1.71 mole of magnesium iodide. Then after the reaction was complete, he tells the TA, what's the TA? The technical assistant or the teaching assistant, that he got a yield that is 84.5%. So the question is, how many grams of magnesium iodide did he make? So notice that we have the percentage yield, and then we have what was given. What is what was given? 1.71 mole of magnesium iodide is what? Should. He said he should, meaning that he didn't. He should. So that means that is the theoretical yield. So meaning that we have the theoretical yield, we have the percentage yield. What we need is the experimental yield. That's what he actually got. And from what he actually got, we can now get the mass. If we get the mole of what we actually got, we cannot get the mass from the mole, given that we know that mass is equal to molar mass multiplied by number of moles. So let's just get right into it. So given the percentage, we just multiply this by the percentage divided by 100, and we have 1.44 mole. It's just straightforward from the formula, because the actual yield is what is here. Do this, multiply this way, divided by 100, we get our value. That's 1.44. And when we get the 1.44, we just multiply it by the mass of magnesium and 2 moles of iodine added together, which is 278.1. This over 1 here was just over 1 of the same, the mole of the same magnesium iodide. Then you multiply that through and you get 402. So notice that again, 278.1 is the, on the periodic table, you see the mass of magnesium and then the mass of iodine, multiply by 2, add them together, you get that value. So that's it. So it means that the mass as requested is 402. Notice that the question did not say what is the actual yield or experimental yield. The question said the mass, so hence we had to go further with the calculation. So don't just run off like that when you get your actual yield. So that's it for the course. So at the end of the day, you knew how to work out moles to mass. We didn't do molarity, so that's out of the way. We did smallest formula, we did the equivalence, we did the percentage composition, we did the simplest formula and chemical analysis and balancing of the equation, and we did the limiting reactant, the masses of the product on reactant. So that's it for this course. So look forward to the quiz 2, and the quiz 2 is going to involve 50% of lecture 3 and 25% each of lecture 1 and 2 respectively. So thank you for your time and study, take notes, and all the best. See you on the next lecture, or see you in class for those of you that are going to be in the face-to-face class. Bye.